Let me give you a summary of what we've done so far regarding the power rule here. When we first started our calculus, we could easily differentiate x to the x squared by following this. We could easily differentiate x to the power 3 by following this. But when it got to x to the power of, let's say, 7 here, this bit is really tedious. You have to get x plus h and then times it by itself 7 times. It got really tedious. So we would jump to the binomial expansion. So by us using the binomial expansion, we prove that this power rule here works for when n is a positive whole number. Okay, and then by using a bit of common sense, even when n equals zero, here, the power rule here will still work. Even it will still work. The power rule will still work even when n equals zero, because if you put zero into this n here, you will have x to the power 0, which is 1. But when you try and differentiate 1, that would give you 0. Now looking at on the right hand side, at the moment you've got one block multiplying with another block. So even when n equals 0, if you put 0 into this block here, you're going to have 0 times something. Well, 0 times something is pretty much 0. So the point is that this power rule here still works even in the case of when n equals 0. Okay, so the binomial expansion here shows us that it works when n equals all these here, and then by using a bit of common sense, it will also work for when n equals 0. By the way, the binomial expansion actually will cover it was when n equals 0, the binomial expansion will still work. So by us using the binomial expansion, it does actually take care of the 0 itself. Well, anyway, up to this point here, we know that the power rule works for when n equals 0, 1, 2, 3, and so on. Okay, and then in the case of x to the power of a negative number, we had to use the quotient rule. Okay, so to prove that the power rule works when you have a power of a negative number, we have to use the quotient rule here. And then it's blah blah blah. I've done several videos on this, so if you don't understand it, then well, it's basically following the quotient rule here. It's blah blah blah. You would get to this stage here, and then from this you can see that whenever you want to differentiate a negative number, you move this down here. That's this bit here, and then the negative number itself gets minus by 1. So by us using the quotient rule here, we prove that it will work for negative numbers as well. So the binomial expansion proves that it works for all these, and then we have to use the quotient rule to prove that it will work for all of these. Okay, and now for the case of a fraction, x to the power of a fraction, let's say x to the power 3 over 7, we have to use implicit differentiation. Okay, so we would have to blah blah blah, and again several videos on this already. So you would get to this stage here, and then when you get to this stage here, you can see that whenever you want to differentiate a fraction, x to the power of a fraction, this gets moved down to here. That's why you get this here, and then the fraction itself gets minus by 1. So by using implicit differentiation, we prove that it will work, that the power rule here, this here will work for where even when n is a fraction. So it will work for a rational number. Okay, and then so far, hang on. So far, we wanted to understand when this thing here works. For what condition will n must need to be in order for this to work? Well, by using the binomial expansion here, when n is a natural number here, it will work. When n is a natural number, and even when it's a 0, the binomial expansion also proves this here. But then to enter the negative realm, we had to use a quotient rule here. Okay, and then for a rational number here, we had to use implicit differentiation here to prove that the power rule here works even if this is a rational number. Okay, so hang on. So binomial expansion proves this. Binomial expansion proves this here. quotient rule proves this here, and implicit differentiation proves this here. Our next step is will it work for all real numbers? So for example, suppose you have x to the power of, let's say, pi. Now pi, you cannot express it as a fraction. It goes on and on forever. So will we still be able to use the power rule for x to the power of pi? Or well, don't forget, if you have x to the power of, let's say, 7, 3, 4, hang on, even if you have, let's say, hang on, let me think. Even if you have, let's say, even if you have x to the power of 0.73742, and then it terminates here, this here you can still use the power rule, because you can also express this as a fraction. So imagine this as being over 1 here, and then times top and bottom here by 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. So if you times top and bottom here by 100,000, 1, 2, 3, 4, 5, yeah, by 100,000 here, then you can express this as a rational number. Well, my point here is that even if you have x to the power of, let's say, even if you have x to the power of 2.735 here, you can still use the power rule. But the thing is, if you have x to the power of, let's say, pi, you see pi you cannot express it as a fraction. So will the power rule still works for x to the power of pi? This here, you need to build up more knowledge in order to be able to answer this question. So we still have to develop more skills in order to answer this question. Okay, but definitely when you have x to the power of a fraction here, it will still you can use the power rule. But in the case of x to the power of pi, take my word for the time being that yes, you can do it, but to actually understand why you can do it, you need to develop more knowledge. Okay.